So, good evening, everyone. I welcome you all to the 11th live session of the NPTEL online course, Basic Principles and Calculations in Chemical Engineering, a course instructed by Professor S.K. Majumder from IIT Guwahati and myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, who will be conducting this live session. So, some information about these live sessions is that these have been conducted every week on Tuesday from 7 to 9 p.m. for the duration of this course. The recording links of these sessions has been made available to you, and you can also access them through my YouTube channel. The structure of these sessions is that firstly we'll go through the overview of the lectures for the corresponding week, which is the week 11th this time, and then solve some sample problems related to the assignment for this week. So, in lecture 32, we dealt with the process degrees of freedom. So, why do we need these process degrees of freedom? So, suppose you have a chemical process unit, and there is a problem statement given to you so as to basically either optimize the yield or increase the yield, um, uh, optimize the flow rates or anything. So in that chemical process unit, there may be some problem statement given to you, and if you want to solve this problem statement using some computer codes, computer codes, so you need to know if that specific problem is solvable or not. So that's why you need to do the degree of freedom analysis. And for a reacting system, the number of degrees of freedom, or NDF, is equal to this formula given here. So in a process, or in a suppose in a unit, basically there may be some knowns or there may be some unknowns. So this is basically the variables that are unknown, so number of unknowns plus number of independent reactions that are occurring. You subtract the number of independent equations. What are these? We'll get to know in the subsequent slides. And you also subtract a number of useful auxiliaries related. So from this degree of freedom analysis, if the NDF is equal to 0. So basically what you are doing in this formula of NDF is basically you are subtracting the number of, it's a difference between number of unknowns and number of equations. So if number of unknowns and number of equations are equal to each other, so NDF will be 0. So it is a completely defined system and it will have a unique solution only. If suppose the number of unknowns, I can write it here as well, number of, number of unknowns minus number of equations. A broad sense for NDF, you can think it like this only: number of unknowns minus number of equations. So if the number of unknowns and number of equations are equal, so the result will be NDF is equal to 0. So the system is completely defined and you will have a unique solution or just one solution for that problem statement. NDF is greater than 0. That means the number of unknowns are greater than number of equations. So it is an underdefined equation. You need more equations. You will have to add more equations so as to completely define this and get a unique solution. Otherwise, if it is underdefined, it will have an infinite number of solutions. Suppose there is x plus y giving some 5 and x plus 2x, or but okay, so x plus y is equal to 5. So this is, suppose, some equation uh, you have, and you see that there are two unknowns here, so you require one more equation here so as to get a solution. You can have a number of multiple values here, so x can be 2, or then y will be 3, x can be 1, then y will be 4, x can be minus 1, then y will be 6. So it has a number of solutions. So if the system is underdefined, so it will have an infinite number of solutions. If NDF is less than 0, so that means that the number of equations in a broad sense is greater than the number of unknowns. So basically, you're over defining the system. There are too many constraints in that system, and using all of those equations, the system cannot be solved. So this is why you need to have degree freedom analysis so as to know beforehand if you have a system, if you have a and there you need to solve it. So whether it is either solvable or not, you can do this by degree of freedom analysis. So I talked about independent equations in the previous slide. So these are those equations which you cannot derive it by adding or subtracting the other equations. So example I can give you is that suppose x plus y is equal to 3. So 2x plus 2y is 6. There are two equations and two variables. Okay. But you see that if you multiply this equation by 2, okay, so you get basically this equation only. So these are not solvable. So you need to have only independent equations in your degree of freedom analysis. So only independent equations are included. So the that system which I showed, x plus y is equal to 3 and 2x plus 2y is equal to 6. So this is the only independent equation here. This will not be considered. Okay. So this is dependent on this only. Or if you get, suppose there is an equation x plus y is equal to 1, and then 4x plus 3y is equal to suppose 4, and then there is another equation if you add these, so it will be 5x plus 4y is equal to 5. So these two are independent equation. This is a dependent equation on these two. Just an example here. So these independent equations can be material balance for a non-reactive process. So material balance can be, suppose this is a unit for a non-reactive. Suppose there is a separator here and it is giving us two streams, suppose, and this is the feed. This is P1, this is P2, suppose. So whatever the overall material balance or the component material balance will be there. So suppose this feed has two components, x1, x2. These are the concentration in either mole fraction or mass fraction. So this will also have this may be a pure component or this may have both these components as well, and P2 will also have both these components. So either the overall material balance or the component material balance. But mind you that you can obviously see that suppose this is x1f and this is x2f. This is P1, so it will have x1 in P1 and x2 in P1. This will have this is P2. I'll make a better diagram here. So this is P1. So I will have x1 in P1 and x2 in P2. So and this is F, which will have sorry, x1 in F and x2 in F. So I have another stream P2 which will have x1 in P2 and x2 in P2. So there will be three equations here, correct? So one overall material balance and two component material balance. But if you want to consider it as an independent equation, so you will only consider, so in total there are three equations. But if you add them up, I mean, if you add these two component material balance, you will get this overall material balance. So basically, you have a system of three equations, but one of them is dependent on the other two. So you will have to only consider out of these three equations only two equations. Okay. So material balance for a non-reactive process, energy balance, given process specifications if there are any specifications, physical properties and laws, suppose inert gas, ideal gas laws or density relations, then physical constraints if there are. So suppose the summation of all these physical constraints, you can see that because these are mole fractions, so the summation of these two will be equal to 1. Then the stoichiometric relations for systems with chemical reactions. So process degrees of freedom. What are for a process? So suppose this is a system of there is a mixer and then there are two distillation columns. All are attached in series. So you see that the degree of freedom analysis for a suppose for a multi-unit system can be conducted for the overall system. So the boundary, you need to define the boundary of a system. If it is an overall degree of number of degree of freedom that you need to compute, then it will be for the whole system. So the inlets for the overall system are these 1 and 2 stream. The outlet are 4, 6 and 7. Okay. Now, if you want to consider it for a particular unit, suppose this mixer. So you need to draw the boundary. You basically you need to define your system. So for defining your system, you draw this boundary. So after drawing this boundary, you see that the inlets are 1 and 2, but the outlet is now 3 only. Now for then the unit 2, the second unit, the first distillation column. So again, the inlet is third stream while the outlets are 4 and 5. And same goes for the second distillation column. The inlet is fifth stream and the outlets are 6 and 7. So for the degree of freedom analysis, this is the basically flow of the uh, process flow sheet basically given, or you can say the steps that are involved for the degree of freedom analysis. So first, after understanding the problem statement correctly, you draw the process flow diagram, then label each stream with the components present. Okay. Write the independent equations for each unit, then mark the unknowns, then write the auxiliary equations if any, and then perform the DFA. So if you see in this system, you have drawn the flow diagram first, and then after this is the flow diagram. So, and after that, you are writing all the components that are involved. You are labeling all the streams. You mark the unknowns if there are any. You write the independent equations for each unit. So independent equations will be material balance mostly, or if there are any, because this is a pure separation, mixing and separation. So there are no reactions involved here. So it will only have material balance equations, and if there are any auxiliary equations which are given in your problem statement, you write that and then perform the DFA. Okay. So we move on to the 33rd lecture. So in that we discuss the process flow sheeting and codes. So what is process flow sheeting? It is used to perform the computer-based calculations of the steady state heat and mass balance, sizing and costing for a chemical process. Um, so in the process flow sheeting, you would require an equation solving program which solves your set of linear and nonlinear equations. So the one of the important requirement is that the sufficient specifications need to be required to be given for your problem statement to take up all degree of freedom. So it has to be solvable. Then it includes various library models which perform either optimization, roots of equation, give you differentiation, integration, and other operations. So the techniques to solve these equations can be either a direct method or an iterative method. So direct method will give you a direct numerical value. So you perform this mathematical operation just once and you get the final answer. So it is basically usually used Gauss elimination method. While in iterative method, you need to do the equation again and again, and you need an initial guess here. Sorry, requires an initial guess. It will not give you a direct answer in just one mathematical operation. You get initial guess. Sorry. So after you perform the mathematical equation, suppose you get some answer, let it be x1. But you need to put this again in your problem equations of your problem statement to get another solution, which will be x2. And then keep on doing it until you get a probable answer. So what is the most probable answer? That means you need to set some convergence criteria. And when you reach that convergence criteria, so then you say that your solution is achieved. Again, in process flow sheeting and codes, you can do it by either the spreadsheet programs or the flow sheeting programs. So spreadsheet programs make use of these spreadsheets basically. So it has a large arrays of or rows and columns of your data basically. So makes use of spreadsheets. Spreadsheets, that means your the most common example for that is your Excel program. And the flow sheeting programs, they can be either equation oriented method of flow sheeting or the modular method of flow sheeting. So in equation oriented method, the equations are solved either sequentially or simultaneously, either or in the modular method of flow sheeting, it is a collection of modules and the equation for each subsystem is collected together. And the module of these in this method can be used in isolation from the rest of the flow sheet. So we start with the sample problems for the week 11. So first question is, for a solvable system with unique solution, the NDF will be greater than 0, NDF will be less than 0, NDF will be equal to 0. So what will be the correct answer here? So for the first question, for a solvable system with unique solution, the NDF will be greater than 0, NDF will be less than 0, or NDF will be equal to 0. What will be the correct answer here?
NDF equals to 0.
Okay. So, yeah, you are correct, because NDF, if you see in the broader sense, it is basically number of unknowns minus number of equations in the broader sense. So, if number of unknowns is equal to number of equations, so the system is uh, uh, properly defined. So, completely defined basically, and you can say that it is a solvable equation, solvable system basically, sir, with a unique solution. Yeah. So next question, for an underdefined system, NDF greater than 0, NDF less than 0, or NDF equal to 0. What will be the correct answer here? For the underdefined system. So as I discussed in the previous slide, so NDF is, in a broader sense, number of unknowns minus number of equations. So underdefined means there are more unknowns than number of equations. Okay. So underdefined means that there are a number of unknown variables, but you have an insufficient number of equations. So it is, you need, basically you require more equations to define your system. So it is called an underdefined equation, underdefined system, sorry. And in that case, NDF, because this is number of unknown is greater than number of equations, so NDF will not be equal to 0. It will be basically not be equal to 0, and NDF will be greater than 1. So A part is the correct answer here. Next question, for an overdefined system, the NDF is greater than 0, NDF is less than 0, or NDF is equal to 0. What is the correct answer here? What do you think is the correct answer here? So for an overdefined system, as I have told you, that in this case, number of equations will be greater than number of unknowns. So in that sense, NDF will be less than 0. So B part is correct here. Overdefined means you have a lot of equations. So suppose you can say that x plus y is equal to 10. 2x plus y is equal to, you can say 15. Then again you have another equation, x plus 3y is equal to, suppose, 20. So you have two variables only, but you have three equations here. So it is an overdefined system. So this is basically a not non-solvable system. So NDF will be less than 0 because number of equations is greater than number of unknowns. Here there are only two unknowns, but equations are 3. Next question, calculate the number of unknowns in the given figure. So this is some process going on here, and these are the inlet stream and these are the outlet stream. You are given some flow rates, and you are given the composition as well for the each stream. So what are the number of unknowns? How many number of unknowns are there in this figure? Can you tell me? Can anybody give me the answer for this? How many number of unknowns are there? So as you can see, the numerical values for um, all these variables are given to us. However, for M1, M3, and M4 are not given to us. So these are the number of unknowns here. So the number of unknowns is 3 only. Next question, calculate the NDF for the given system. So we are given this single unit itself, it's a distillation column. So we know the feed flow rate, but the we don't know the inlet composition of these A and B components. Then we know the distillate flow rate, which is 70 mole per hour. We don't know this W, and we don't know this. We don't know this composition of A in the residue, so or in the bottoms. So number of so for the NDF we write that number of unknowns my because this is a non-reacting system, so you don't add any independent reaction, minus number of independent equations minus number of auxiliary relations. Okay, so how many number of unknowns are there basically? So this is one unknown, this is one unknown, and this is one unknown. Why I am taking only these three unknowns only? However, there are, if you can see, 1, 2, 3, 4, 5, 6. 6 unknowns are there because this XAD can be found out using this XBD can be found out using XAD. So XBD is basically 1 minus XAD. Okay, so basically, if you go by this logic, so there are 1, 2, and this W is also an unknown. So 3 unknowns minus the number of what are the number of independent equations. So independent equations here will be the material balance. So out of this material balance, you can take, so the number of independent equations for a material balance is usually equal to number of equation uh, sorry, number of independent material balance equation is usually, so I write it here, usually number of independent material balance equation is equal to number of components. Okay, so how many components are there here? 2. So the number of independent material balance equation here will be 2 only. Or you can say the total material balance equations are 1 overall material balance and 2 component material balance. But as I have told you, if you sum these two, you get the overall material balance. If you subtract OMB, if you subtract this one of these component material balance from OMB, so you get another component material balance. So basically, these there are 3 equations. However, only 2 are independent, while the third one is dependent on the other. Okay, we don't care what equation we are taking, what equation we need to consider, we only need to care how many number of independent equations are there. Okay, so basically 2 independent equations are there. Okay, so 2 independent equations and any number of auxiliary relations, so there are none, so you get 3 minus 2 is equal to 1. Or another way to do this is that 1, 2, 3, 6, 7, 1, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So 6, 6 minus 2 you take, and then 1, 2, and 3. Yeah. So another way you can do this is, if you consider all of these relations, if you consider all of these unknowns, so 1, 2, 3, 4, 5, and 6. So 6 unknowns are there. Again, the material balance equation will be 2 here only. Independent equation here will be 2 only. But if you also consider these relations as well, you can consider these as auxiliary relations as well. So the for XBF, it will be 1 minus XF. So 1 minus 1, another from here minus 1. So and another from here minus 1. So it will be 6 minus 5, again 1. So the number of degree of freedom for this system is 1. So can you tell me if this will have a unique solution or a infinitely many solutions, or you cannot solve it? What will be the can anybody tell me? Because the NDF here is you get is equal to 1. So is this solvable firstly or not solvable? Will I get unique solution or infinitely many solution or no solution? What will be the correct answer here? Can anybody tell me?
Ma'am, the answer will be unique solution.
Are you sure?
Yes, ma'am.
The NDF is equal to 1.
Ma'am, one is for unique solution, no?
No, 0 is for unique solution. I can show it to you. See, I've solved this question as well. For a solvable system with unique solution, NDF is equal to 0. Or you can see from this slide as well. Completely defined, NDF is equal to 0, completely defined and unique solution. The logic behind that is, I can again explain it. So usually people make this mistake, NDF is equal to 1 is not a unique solution because NDF it basically is NDF greater than 0, right? NDF is equal to 1 is NDF greater than 0. So that means underdefined. So it will have infinitely many solutions. Okay? Did you get it? Or I can write it here as well. NDF is in a broader sense is basically number of unknowns minus number of equations. So here number of unknowns, if these number of unknowns are greater than number of equations. Okay. So basically you need more equation to solve your number of unknowns. Okay. So in this case you will have infinitely many solutions. Do you get my point?
Yes, ma'am.
Okay. Or I can give an example as well. Okay. So a basic example, suppose there is a system, the equation given by it is there are two variables x plus y is equal to 10. Okay. So now there are two variables, but the equation defined for this system you get is only one equation, x plus y is equal to 10. So now there are two variables, but only one equation given. So here x can take any value and y can take also any value to satisfy this equation. So if x is 2, then y will be 8. If x is 6, then y will be 4. So there can be a number of solutions. Or suppose if you say that x is 6.1, so this will be 3.9. So there are infinitely many solutions for this system. Why? That is because number of unknowns is greater than number of equations. So in that case, NDF will be greater than 0 and it will be an infinitely many solution case. Okay. Next question. The reaction 3A gives C takes place in a reactor. How many independent molecular species are involved in the process? So how many independent molecular species are involved here in the process? So the correct answer here is basically 3A gives C, so A and C are involved, as well as there is some, you can say it is an inert molecule because inert species because the flow rate for the this species B is the same at the inlet and the outlet. So it may not be taking part in the reaction, but it is involved in the process as well. So the independent molecular species involved are three here: A, B, and C. So three. Next question, compute the overall NDFs for the given system. So for the overall NDF, you basically need to draw a boundary around the whole system. Okay, so this is your boundary. So you can see that the unknown streams are 1, 2, and 3. Now here you can say that the flow rate is suppose F3 and the concentration is you can say XA is XA comma 3 and xb comma 3. Okay, so you see, you need to calculate the overall NDF. So I can write the formula here. NDF is, because, and mind you, this is a non-reacting system. Although the information is not given here, this is a non-reacting system. Okay, so NDF, you can say that number of unknowns, you can say, then plus if there are any number of independent reactions, okay, then minus number of independent equations, and then minus number of any auxiliary relations. So here there is no such independent reaction, so number of unknowns minus number of independent equations minus number of auxiliary relations. So here we see that overall NDF for this will be number of unknowns is 3, then minus number of independent equations will be 2. Okay, number of unknowns is 3, F3, XA3, XB3, and you can say auxiliary relation can be XB3 is equal to 1 minus XA3. So again minus 1. So answer is 0. Okay, the overall NDF for this system is 0. Okay, next question. Compute the NDFs at the mixing point for the given system. So what is the mixing point here? This is the mixing point. Okay. So you can say, you can write this. I am drawing it here. So this is stream 1. This is stream 2. And this is, we are given 30 kg per hour. And then 0.3 kg A per kg, and then 0.7 kg B per kg. Okay, so the number of unknowns here will be, again, this will be, suppose F1, XA comma 1, XB comma 2. This is again F3, X A comma 2. Oh, sorry, XB comma 1 only. And then this will be XB comma 2. So 1, 2, 3, 4, 5, 6. 6 unknowns again. Okay. I write the formula again here. Number of unknowns, because there is no reaction again here. Number of unknowns minus number of independent equation minus number of auxiliary relation is your NDF, non-reacting. So there are 6 unknowns. And then the material balance, you can say the material balance or the independent equation will again be 2, because there are 2 components. And then the auxiliary relations will be useful auxiliary relation, again 1 and 2. So 2, 6 minus 4, it will be 2. Okay. Or another way to do this is, you don't consider one of these. Okay, and then you don't have to consider this auxiliary relation as well. So another way, or a later way, is that you can say that the number of unknowns are 4. Okay, and number of independent equations are 2. You don't need to consider the auxiliary relation. So 4 minus 2 is again 2. Then we need to compute the NDFs for the first unit for the given system. So this is the first unit given here. You see that these are knowns. The unknowns here is F1, X A comma 1, and XB comma 1. So number of unknowns again will be, NDF will be number of unknown minus number of independent equation minus number of auxiliary relations. So you see number of unknowns is again 3. The number of independent equation again will be 2, and number of auxiliary relation is 1 here. So you get 0. Okay. Next question. compute the overall NDS for the given system. So now you see that there is a reactor involved, so this will have a reaction as well. So you need to compute the overall NDF. So basically, you draw the boundary here. Okay, so what are the number of unknowns here? So I write the NDFs as well. Formula for NDF, number of unknown minus, plus number of independent reaction minus number of independent equation minus number of auxiliary relation. So number of unknown, how many number of unknowns are there? So 1, 2, 3, 4 and 5. Number of independent reaction going on here is this, one reaction is going on here, so 1, and then minus number of independent equation. So how many number of independent equation will be there? So overall, so if you don't count overall, so 1, 2, 1, 2, 3, 4, 5. So 5 again, okay. And number of auxiliary relation. So you can write it as 1. So 6 minus 5 minus 1, 0. Okay. Next question. Draw the flow diagram for the problem statement. So you are given a problem statement. You need to draw a flow diagram. So it says a mixing unit receives 2 streams. So there is a mixing unit. So first we draw that. Okay. A mixing unit receives 2 streams. One containing equivalent amount of water and methanol. So suppose this is F1 and this is F2. So one containing equimolar amount of water and methanol. So I can write this as XW, F1 is equal to 0.5, XM, F1 is equal to 0.5. And the other with 10 moles of 10 moles. So this F2 is basically 10, of which 40% is aqueous methanol, not aqueous methanol, you can say. So XM F2 is 0.4, and then XW F2 will be 1 minus 0.4 is 0.6. Okay. The mixture enters the first separator. So there is some mixing going on here. It enters the first separator. So this is entering some separator, or you can say distillation column, because methanol water mixture. So mixture first separator to produce 2 new streams. The top contains, so there is a top stream and there is a bottom stream. Okay, so the top contains, you can write this stream as F3. So you are not given any information about this mixture, so you can write this as F3, and then again XW in F3 and XM in F3. Okay. The mixture enters the first separator to produce 2 new streams. Okay, so these are 2 new streams. The top contains 70 mole percent methanol and remaining being water. So you can write this new stream as T1, and this has XWT1, which is 30. Oh, sorry, not 30. You can write it as 0.3, and XM, T1, which is 0.7. Okay. Now the bottom stream contains 70 moles. So this B1 is 70, and so there is no further information about the composition. So XM, B1 and XW, B1. Okay, so it again enters another separator, or you can, leaving some space because there is some text here. So bottom string, okay. So enters another separation, second separation unit. So again, it may have two streams, I'm assuming, but it does. So the top product contains equimolar amounts of both compounds. So again, no flow rate given here, T2, and equimolar amounts of both compounds. So it will be X W comma T2 will be zero point 0.5 and X M comma T2 will be again 0.5. Now, uh, while the bottom stream flow rate and composition is unknown, so all are unknown here. So B2 X W comma B2 X M comma B2 all are unknown. So this is how you draw the flow sheet. So you have written all the variables that are involved. You have shown how the process flow goes on. So this is how you draw the flow sheet. Okay. So whatever I drew here, I have a pictorial depiction of that here shown. So now you know this question, you know the flow sheet, you have drawn the flow sheet. Now you compute the NDF or the number of degrees of freedom. So overall NDF for the system given a basis of 100 moles of M plus W feed and the amount of both top products is equal. So what this means is that F1, the F1 given here, F1 is equal to 100 because F2 is given to us as 10. So F1 is equal to 100. So we know this from the given question. And the amount of both top products. So this is top product T1 and T2. So this is equal. T1 is equal to T2. Okay. So we need to compute the overall NDFs. So if you see, we need to draw this boundary again. So this will be our boundary. Okay. So inlets are this F1, F2, outlets are T2, T1 and B2. Okay. So you need to compute the number of degrees of freedom. Again, this is a non-reacting system. Only mixing and separation is happening here. No reaction is involved. So again, the NDF formula will be number of unknowns minus number of independent equations minus number of auxiliary relations. So number of unknowns here, how many number of unknowns are there? So if you count 1, 2, 3, and 4. You are not counting this because you can either count this and add an auxiliary relation or I'm leaving it here. So number of unknowns are T1, T2, B2 and XW, B2. So 4. Number of independent equations. So now there are two components, so two equations. Then number of auxiliary relation. We are given this relation T1 is equal to T2. So minus 1. So 4 minus 2 minus 1. It will be 4 minus 3, 1. You get the answer as 1. The overall degree of freedom for this system is 1. Next question. Compute the NDS for the mixer. So we are given this mixer here. So again you draw the boundary for the system. So this is the boundary. And then you need to compute the number of unknowns. Number of unknowns given here are, you can take it as 2 minus again two two independent equations. Okay, so 2 minus 2 it gives us 0. Why two number of independent equations here? Can anybody tell me? Can anybody tell me why two number of independent equations here? Number of independent equations are two because of the you will only consider here material balance equation. So material balance equation mm, are basically three equations, but only two will be considered because these are three, but one of them is dependent on other two. So you only consider, that's why two equations. Okay. So you get the number of degree of freedom for the mixture as 0. Next question, compute the NDS for the first distillation column given a basis of 100. Okay, so we know the basis, but I don't think that will be necessary here. So, so you see here, this is the first distillation column, and you draw the boundary to define your system because that is what your system is as per the given question. So again, you count the number of unknowns. So number of unknowns is you see 1, 2, 1, 2, 3, and 4. So four unknowns are there. Okay. Number of independent equation again will be 2. Number of useful auxiliary relations. So we are given the top product of T1 is equal to T2. But is it useful here? Because this is our system. And this T2 is not involved here in any case. So it is not a useful auxiliary relation here. So you will not consider it here. So 4 minus 2 will be 2. Okay. Last question, compute the NDS for the last distillation column given a basis. Again, okay, if this is useful or not, we'll see. So you again draw the boundary. Okay, so you count the number of unknowns. 1, 2, carefully count the number of unknowns. You start from the inlet. 1, then you go to the two outlets. 2, 3, and 4. Again, 4 unknowns. Number of independent equation again 2. You get the answer as 2. Any questions, anybody?
Yes, ma'am.
Yeah, tell me.
Ma'am, actually, a question has been given in our assignment that what is the disadvantage of using a spreadsheet program? Ma'am, then what will be its answer?
Actually, I cannot discuss the assignment answers with you right now. I can only discuss them when you have submitted them. I cannot discuss them beforehand. Sorry. So I cannot directly tell you the answer here. Sorry.
But can you means what would be the probable disadvantage of using a spreadsheet program, ma'am?
Spreadsheet programs.
Yes, ma'am.
Okay, so spreadsheet programs is basically you need to enter all your data. Okay, and then it is used. I can tell you that it is used for simple equations usually, and that's it. I can tell you that much. I can give you that much hint.
Okay, ma'am.
Did you get my point?
Ma'am,
Hello?
little bit.
Yeah. So simple
Yes,
systems,
ma'am.
simple equations, it is usually used for that. I can tell you only that.
Okay, ma'am.
Okay. Any other question? So if there aren't any further questions, I'll go ahead and close the session for today. Thank you everybody for joining.
Thank you, ma'am.
Thank you.